Good morning, folks. This is my first problem in my Part 2 series on applying Newton's laws in advanced situations. And I picked this problem because this one in particular, I remember giving me difficulty when I was an undergraduate, and I never really understood why until recently. So if you're watching this video, I imagine you're having trouble or difficulty with this problem too. So I'd like to show you not only how we can solve the problem, but why you are running into those roadblocks in the first place. So it really comes down to being able to do the problem in two different ways. And there's really an easy way and a hard way. And I'd like to start off doing things the hard way so you can see and appreciate the approach of the easy way. So we have this problem here where it's a horizontal wire that is holding a solid uniform ball, and we're given the mass m. It's holding it in place on a tilted ramp that has a 35-degree angle relative to the horizontal. The surface of the ramp is perfectly smooth, so we don't have to worry about friction. And the wire is directed away from the center of the ball. And we have three tasks. Draw the free body diagram, solve for how hard the surface of the ramp pushes on the ball, or alternatively, we're going to solve for the normal force that's acting on the ball, the normal force of the ramp. And finally, what's the tension in the wire? So let's start off by drawing the coordinate system for the free body diagram. And remember, this is the hard way, so I'll even kind of label this up top. Hard way. Okay? And I'll go through the hard way, parts A, B, C, and if you're interested, you can see what the easy way is, but the answer is still the same. It just kind of depends on how you are setting up the coordinate system for this problem. So let's set up the coordinate system so that x and y are at a slant. You can kind of picture it as if I drew a coordinate system on the center of the ball like this, here in gray. Here over on the right is where I'm going to draw the actual vectors, though. I just want it to be apparent why these axes are kind of slanted instead of the regular up and down coordinate axes that we're familiar with. And when it comes to this setup, there are only three forces acting on the ball. So three forces acting on ball. And what are those three? Well, one of them is the weight. That's always the case for objects with mass. We have the normal force, and that was from the ramp. Okay, so there's two, one left, and that one would be the tension in the wire. Those are the three forces that are acting on this ball. That's it. So we know when it comes to weight, that typically acts straight down. And so I'll draw it with this purple arrow here and label it W for weight. So there's that one. We need to draw the normal force from the ramp. Well, the normal force of the ramp is perpendicular to the surface of the ramp. So I'll draw it in this blue color here. And that will go off along this line here. Okay? It's perpendicular. So if I draw a 90-degree angle piece here, it's perpendicular to the coordinate axes representing the ramp. Okay? We'll say that this is plus x, pardon me, x, and this one up here is plus y. So we've got the normal force up here, the weight down here, and we need to also represent the tension in the wire. And if you notice in this picture, the wire just points directly to the right. So I'm going to draw it directly to the right, like this. Oh, maybe not. One more time. There we go. Perfect. Okay, and I will label this as T, representing the tension in the wire. And as we can see here, the tension appears to be at an angle relative to the x-axis in this coordinate system. And the weight appears to be at an angle relative to the y-axis in this coordinate system. And they're actually the same angle as the one that we were given, the 35 degrees. I'm going to make this distinction here. I'm going to say that theta is equal to 35 degrees. That way you'll know what these angles are, and I don't have to write 35 a bunch of times. Theta takes up less room, so that's a little bit nicer. So that is our free body diagram of the situation. We had the weight pointing directly down. We said that was accounted for. We said that the normal force from the ramp acted entirely perpendicular to the x-axis in this coordinate system, so that one's taken care of. And then we also have the tension in the wire. So all three of those are taken care of. So in this portion, part A is done, right? That's it. Boom. So now our job is to figure out part B and part C. Figure out the normal force and figure out the tension in the wire. And this is where you will realize why I've called this the hard way. I'm going to do this on a fresh page just so we can kind of see what's going on here. We're going to start with Newton's second law that you've seen before. Nothing really changes in that aspect. We should approach this in the x-axis and the y-axis separately. So in fact what I'll do is I will move this over so you kind of see where my starting point was here. And we have two things we have to do. We need to do the sum of forces in the x direction. And if I kind of go back to the slide that we were on here, let's see at where we are in terms of forces for the x direction. So we want to look at all the forces that are acting along this kind of diagonal direction. That's what we've said the x direction is. So I see one piece that is acting in the x direction, and that would be if I draw the other pieces of this triangle representing the tension vector. Here we have t cosine of theta on this side right here, which is acting in the positive x direction. So if we go back to this expression here, we can say, okay, the sum of forces in the x, we have t cosine acting in the positive direction. What about anything else acting in that direction? Not positive, but notice if I draw the triangle representing the weight vector, I have w sine theta here acting in the negative x direction. This length right here, this kind of lighter purpley color. So we have sum of forces in the x is t cosine theta minus w sine theta. And normally we would say this is equal to ma, but we were told, if I go back to this other slide, this wire is holding the ball in place. It's not moving. There is no acceleration. So that means that t cosine theta minus w sine theta has to be equal to 0. And we can easily just move this piece over and conclude that t cosine theta is equal to w sine theta. And we can get a very easy expression for the tension. If we divide both sides by cosine, I get w sine theta over cosine theta. And we can rewrite this as w tan theta. And in fact, we can go even further because we know that theta is equal to 35 degrees. So we have w tan of 35 degrees. And if we wanted to use a number to approximate this, if I plug in tangent of 35 degrees into my calculator, this would be approximately equal to 0.7 times w. So that was the tension in the wire, part C. We ended up getting the answer to part C first, surprisingly, starting with the x direction. So let's actually circle that. This is answer to part C. Okay. And we can leave this as 0.7 w. That's totally fine. We were given the mass, that's m. We know that the acceleration due to gravity is just g, so 0.7 times w or 0.7 times mg, same thing. This is still the answer to part C. So let's move on to part B. That would be the sum of forces. Ooh, that's a really ugly looking sigma. The sum of forces in the y direction. Let's try that now. If I go back to the previous slide, remember how I broke up the tension vector here, and I said that the cosine part acted in the x direction. Well, that means that I must have t sine theta acting in the y direction. Okay? It's actually in the negative y direction. And similarly, how I broke up the weight vector, and I said this was the sine, then the other leg of this triangle must be w cosine theta. And it is also pointing in the negative x direction, right? If this is y is equal to 0 here, then everything in this regime, every part of a triangle where the legs hang out down here is going to be negative. And vice versa for all the legs of a triangle or vectors that hang out up here, they're going to be positive. So that means we'll have the normal force subtracting this tension component as well as this weight component. So let's fill that in on this part over here. I'm going to move everything over just so that the screen doesn't get overwhelmed. How about that? There we go. So I said we had the normal force acting in the positive y direction. We had t sine theta acting in the negative direction, and then we also had w cosine theta acting in the negative direction. And this tells us when we set it equal to 0 that the normal force is equal to t sine theta plus w cos theta. And you might think that we're done, because if you check back here, let's see, we did this part A, we did part C. How hard does the surface of the ramp push on the ball? We have the answer, but it's in terms of like tension and weight. We weren't given the tension, so we don't know what that number is. We need to find a better way to express this answer. And in fact, I'm actually going to kind of move this over so that my math looks consistent here. we need to find another expression for this. And in fact, we have an expression for the tension. We just solved for it in the part that we solved for C right here, W tan theta. So here is what I think we should do. Let's call the x component equation number 1, and let's call this equation number 2. I'm going to plug equation number 1, the expression for tension, into equation number 2. It's going in right there. And then the idea is that we should end up with an expression that only involves like mass or weight or something like that. We shouldn't have any tension involved. So let's do this on a fresh page. It will require a bit of algebra. So we have this right here. I'll copy and paste it over. Oops. Right here. Okay. So we have this, and we go, this was equal to what? W tan theta. So W tan theta times sine of theta. Let's do it this way. Sine theta plus W cos theta. That looks a little ugly, but forgive me. Hopefully you understand. This is where I've plugged in the expression for the tension. So we have what? W tangent of theta times sine theta plus W cosine theta. We could factor out the weight from both of these expressions, which will give us tangent of theta times sine of theta plus cosine theta. It doesn't really look like we made too much progress, so instead, let's recall the following definition for tangent of theta. That's just equal to the sine of the angle divided by the cosine of the angle. Maybe if we rewrite things in terms of that, we'll get a little clarity. So we have sine of the angle over the cosine of the angle multiplied by the sine of the angle plus the cosine of the angle. We could combine these two pieces here and say that we have W sine squared theta over cosine theta, and we're adding cosine theta. My immediate idea is to add these two terms together using a common denominator, and in order to do that, I would have to multiply this term here, this second term, by 1, like a special form of 1, and it would be the denominator of this first piece in the numerator divided by itself. So cosine theta divided by cosine theta. This is just multiplying this cosine piece that I've underlined by 1. We're not actually changing anything. This will allow us to get a common denominator. So we'll have sine squared theta over cosine theta plus cosine squared theta over cosine theta. And since we have the same denominator in the brackets here, we can bring these together like this. W sine squared theta plus cosine squared theta. Oh, there's a familiar expression there. All over cosine. So we are in luck, because here is another very important identity to remember. Sine squared theta plus cosine squared theta is equal to 1. Same thing if you change these around. Doesn't matter. Sine squared theta. It's still equal to 1. So what we can say is we can just cross out this whole numerator and just say it's equal to 1. So we have W divided by cosine of theta. which is equal to W of cosine of 35 degrees. We finally have an expression that is purely in terms of W and, you know, a number that you can get from a trig identity. So if I take 1 divided by cosine of 35 degrees, I get the following approximation: 1.22 times W. And that would be the answer for B. Right there. So let's go over what we did, which made this the hard way, because we've solved all the parts. We know all the answers now. We drew the free body diagram. I'll kind of get rid of some of these arrows here. We drew the free body diagram in the hard way that was similar to the way the ramp was set up. The x-axis was parallel to the ramp, and the y-axis was perpendicular to the surface of it. And we saw that the normal force doesn't get broken down. Instead, it's the weight vector that got broken down, as well as the tension vector. And here in the second page, you know, we broke this up into the x part and the y part, and we saw that it was pretty easy to get the tension. That was fast. But when we wanted to solve for the normal force, we had to go through all this simplification and trig manipulation to get to the final answer, 1.22 W. So instead, let's try the easy way. And you might ask, well, what is the easy way? Let's go back to setting up the coordinate system. Remember, on the first slide here, I had the coordinate axes at oblique angles, right? They're kind of like diagonals, if you will. Instead, let's keep the coordinate axes kind of like how we're used to. Let's say it was purely up and down, like the familiar x and y that we've seen time and time again. X and y. How would we set up the free body diagram here? Well, we still have the same three forces. That doesn't change. You would have the weight acting straight downward. Let me try to get this more in line with the axis here. There we go. Close enough. All right. So there, and that would be W. The normal force would still point in this direction. That wouldn't change. And we'll still label that with N. But the tension no longer acts at an angle relative to the axes. It acts just straight to the right. Yeah, you'll have to forgive me. It doesn't really line up well with my picture, but it's acting straight to the right. Hopefully you can kind of... man, MS Paint. Come on, work with me. There we go. We can see that it's no longer the tension that is at an angle relative to the coordinate axes. Same with the weight. Now it's the normal force, right? So the normal would have an angle here. And I'll kind of flip back to the first free body diagram, and I'll even copy it over so you can see the difference. You can choose to go the regular up and down, left, right, Cartesian way, or you can choose this way on the right. Notice the difference. Okay? In the hard way, we had the tension and the weight shifted at an angle relative to the coordinate axes, but when we do it the easy way, we let the normal vector get shifted relative to the angle instead. So let's get rid of this picture. I don't want to distract us further. The free body diagram part is done. So part A, part A, done. This would be part A right here. What about part B and C? Would that be any easier? Would there be any difference? Why is this the easy way compared to the other way? Well, if we do the same kind of excuse me, analytical approach with the forces, we take the sum of forces in the x direction, which would be the tension acting purely to the right, and what would be subtracting? Well, if I break down the normal vector here, I've got a side piece, a leg of this triangle acting to the left. This would be n sine theta. Okay, so our force, or our sum of forces in the x direction, excuse me, is equal to t minus n sine theta, and that would be equal to 0. Well, that's a pretty easy expression for the tension. Equals n sine theta. Cool. Let's label this as the first equation. We'll do the same type of check in the y direction. Instead of just purely the normal force, instead we have to take the upwards component of the normal force, which is this one right here, this leg of the triangle. And since the other, the horizontal component was sine, this one is cosine. So what do we have here? We have n cosine of theta minus w acting straight down is equal to 0, which implies that we can move the weight over and very quickly come to the conclusion that n cosine of theta is equal to w, and oh hey, look, we have w is equal to, or excuse me, the normal force is equal to w divided by cosine of theta. We were able to avoid that giant, mountain of work here on this third page to get to that expression, simply because we were able to, there we go, simply because we just changed the way that we set up the coordinate axes. So that's pretty useful. And listen, if I plug equation number 2 into 1, well, then I'll have t is equal to w over cosine of theta times sine of theta. Oh, bam! There's the w tangent of theta that we immediately found in the other approach. So all the answers are still the same. If you plug in 35 degrees for theta and you calculate everything on this slide, you will still end up with the same numbers that we got here on page 2, the 0.7 W for part C, and the 1.22 W for part B. You will still get that. It will still be the same. So this problem is great practice because it exposes us to the possibility of choice. And as we've seen here, sometimes one choice is a huge save on time and effort compared to the other. So in a nutshell, maybe let's just kind of, in a nutshell, very important side note here, something to remember if this is giving you trouble like it did to me a long time ago. If you align your axes or your coordinate systems, if you align your coordinate system such that the acceleration is along one of the axes, one of the axes, the math tends to be easier, as we've seen. So if you align your coordinate system such that the acceleration is along one of the axes, the math tends to be easier. How does this apply in our situation? You might think there is no acceleration because in the x and y directions we set it equal to 0. That's true. The ball is definitely not accelerating due to being sitting still. However, it is still being accelerated due to gravity. It's still being pulled down due to the acceleration due to gravity. I guess a good way to put it is simply because this wire is keeping the ball on the ramp in the same spot doesn't mean that gravity is turned off, right? So in order for us to have an easier time when setting up this problem, we would recognize that, hey, there's no acceleration along the ramp direction, but there is gravity still acting. And if you take the weight vector and you align that force due to gravity along one of the axes, like as you'll see here, the math is way easier. Compare that to here, where we did not have the weight vector aligned with the y-axis. So something to keep in mind. Hopefully you've learned something from this problem. I appreciate you you watching, and I apologize if it was a bit too long, but I hope this helped. Thanks. Take care.